Hello everybody, my name is Noah O'Brien and I'm going to be doing my presentation today on biogenous sediments and their effects on our oceans. So starting off, I'm going to give you an overview of the presentation and what we're going to be discussing. So first off, we'll start off with the question, what are biogenous sediments and why do they matter? Next, we'll go into identifying different types of biogenous sediments, and then we'll work on the interaction between the oceans and these sediments, followed by what is global warming and why should we care, global warming's impact on biogenous sediments, methods to contain the madness, and then a recap. Alright, so biogenous sediments, the basics. Biogenous sediments can be defined as hard exoskeletons left from living organisms that settle and become sediment. Biogenous sediments can be defined as macroscopic or microscopic, depending on how big the organism was. Microscopic sediment is what we will be focusing on today because it is the most prevalent due to the billions of microscopic organisms that can die every single day. The microscopic sediment is made up of very small particles in a mush clay material. When a sediment contains 30% or more of a biogenous material, it is considered what we call biogenic ooze. The four main groups of single-celled organisms that make up biogenous sediments are diatoms, radiolarians, coccolithophores, and foraminifera. Microorganisms' shells, which we will refer today as tests, are mostly settled to the bottom through fecal matter, which is how they can sink so fast to the bottom of the ocean, because these shells are so tiny that it would take them a very, very long amount of time and they would travel a very far distance before they could ever sink to the bottom. So normally how they sink to the bottom and stay localized is they're consumed by another organism and their fecal matter, which is much heavier than the actual test itself, sink to the bottom that way. So now we'll be talking about diatoms. Diatoms are a single-celled organism that have a fully transparent test, and it's made up of a siliceous material. Silica, SiO2, is largely found in quartz. Diatoms are instrumental to humans and the natural processes of nature, and that diatoms use photosynthesis to create their own food and help contribute 50% of the O2 we breathe today. They are also essential sources of foods for a multitude of organisms, from other zooplanktons all the way up the chain to whales. Diatoms have long fatty acids, which help make them extremely nutritious for the organisms consuming them. And when they die, their tests sink to the bottom, where then the siliceous ooze will remain to make a biogenous sediment. Next, we'll be discussing radiolarians, which are bigger in size than diatoms, grouping them in with zooplankton. They can, however, be grouped with diatoms based off the material that makes up their tests. Their shells consist of a siliceous material like diatoms. The holes in their tests are obviously by design because all things in nature are. The organism that lives inside stretches an amoeba-like arm out of the holes in the shell to grab food from its surrounding. To aid them in floating and suspended near the surface of the water level, radiolarians use the points or rays, as you can see on their shells, to become more buoyant. Next, coccolithophores. Coccolithophores are incredibly different from the other two microorganisms that we have discussed so far. Coccolithophores are anywhere up to 100 times smaller than diatoms. Their tests are made up from calcium carbonate, CaCO3, and when the ooze from coccolithophore tests lithifies, it becomes a chalk. A great example of coccolith's ooze is, in real life, the infamous White Cliffs of Dover in England, which is in the picture below the paragraph there. The biggest difference to note about coccoliths is their size and their composition. Next, we will be discussing foraminifera. Foraminifera are snail-like in that they are chambered in their tests. Like coccoliths, they create a calcareous ooze due to their tests containing CaCO3. The most important difference we can make from these four different microorganisms is the difference in composition. Siliceous sediments are not soluble at all in pure water, as it has to be extremely high temperatures for it to dissolve. Calcium carbonate from foraminifera and coccolithophores is not very soluble in pure water, however will be soluble in pure water with slightly more acidic pH or a colder temperature. That is why when discussing biogenous sediments, we must consider the global warming in water pH and temperature levels. Next, I'll just give you a brief overview of global warming, like I'm sure we've all been learning throughout this class so far. How global warming is the unnatural process of the planet warming due to human processes. Global warming is caused by the greenhouse effect when CO2 and other pollutants collect in the atmosphere to absorb sunlight, warming the earth. The main factors in global warming are fossil fuel emissions, obviously. Reducing emissions from fossil fuels is also one of the key parts to reducing global warming. It is essential that our society can contain global warming soon because of the extreme weather events like droughts, wildfires, etc., like we've been seeing. And these events affect everyone, like whether we like to realize it or not, because people will die, homes are being lost, crops are lost by farmers, and the economy is negatively affected by all of this and so much more. Now we'll discuss global warming's effects on our biogenous sediments. There is a big three of factors to consider, which are pH, temperature, and salinity. pH, when we're talking about pH, an estimated 1/3 of all anthropogenic CO2 emissions that are captured into the atmosphere actually dissolve into the ocean. This causes what we call ocean acidification. This impacts the calcium carbonate saturation in the ocean, impacting coccolithophores and foraminifera. Temperature, an increase in the surface water temperature of the ocean has a major impact on nutrients and the natural cycling of the oceans. Longer warm spells and more time between freezing cycles can very negatively affect the available nutrients in the ocean water for the phytoplankton. This also causes the glacial ice to melt, and temperature has also proven to increase growth rates of diatoms, requiring more nutrients to supplement said growth. Microplastics from waste also attribute to the increasing surface temperatures that we've been seeing in our oceans. Salinity. Ocean salinity is largely affected by glacial ice. Glacial ice is mostly freshwater, so when large amounts of freshwater are being added to saltwater, our salinity decreases. Lower salinity in general can affect growth rates and nutrients in the ocean. Overall, changing the natural cycles of anything at an unnatural rate negatively affects the entire environment. The CCD. I wanted to make a separate slide about this just because it is one big part of all of this that I think needs to be focused on a lot. So the CCD, or carbonate concentration depth, is the level at which the water table where calcium carbonate will dissolve in our oceans. Calcium carbonate, as mentioned earlier, is stable in shallow warm water and will not dissolve in it. In colder waters, though, calcium carbonate will dissolve, which is that coccolithophores and the foraminifera we were discussing. The CCD, is obviously an imaginary line, but is pretty much based off of water temperature. This explains why calcareous ooze is more often found in shallow depths or on our shores, whereas siliceous ooze is found in deeper depths in the ocean where it's colder. With ocean temperatures rising, the CCD is going to start moving deeper and deeper. Calcium carbonate is a base considering the pH chart, so this can have an impact on water pH as well at deeper depths. Methods to help our biogenous sediments. Obviously, reducing carbon emissions will help not only our biogenous sediments, but the entire planet as a whole. We can do this by transitioning into more renewable energy sources with solar power, wind power, or hydropower. We can also start to focus on limiting our single-use plastic or microplastic waste that we're creating, because this helps attribute to the water temperature, surface water temperature that is, in the oceans that is on the rise. So overall, a recap, we learned the biogenous sediments are what they are and why they matter. We discussed the different types of microorganisms that die and their tests that sink to make up biogenous sediments. Broke down global warming and what causes it, analyzed the effects of warming has on biogenous sediments with the big three and also in terms of the CCD, discussed what can be done by society across the world to help the preservation of our Earth, more specifically biogenous sediments in this case. And to end it off, here's my works cited, and I hope you all enjoyed.